Okay, so let's start. So we're very excited to have Pavel Kovtun from the University of Victoria telling us about hydrodynamics beyond hydrodynamics. So, Pavel,
thank you.
Please go.
Yes, thank you. Thank you for inviting me to share some of my thoughts on this. And of course, please feel free to interrupt at any time. This is not to be a formal talk, and I'm hoping to learn myself from questions, comments. So I'll start with an introduction, just in case there may be students attending. So of course, hydrodynamics is an established field with long history, many applications. But today I will not talk about applications. I would like to highlight some foundational questions that came to light in the last few years. So what is hydrodynamics? It is basically a set of equations that tell you how stuff flows. Okay, what is stuff? Stuff can be water, air, cold atomic cloud, matter in early universe, electrons in a solid, whatnot. Now, if you're a student and you open book with hydrodynamics, fluid mechanics in the title, I remember my own experience. There are usually derivations and approximations and applications and boundary conditions, and all of this is going to be mixed together. And as a student, you're also learning about vector calculus, differential equations at the same time. It can be hard to see the big picture. Now, the big picture of hydrodynamics is in fact quite simple. It's basically about stuff that is conserved. So it's about conservation laws. So time derivative of some conserved density is equal to minus divergence of some conserved flux. So these are the equations that people would solve in practice for hydrodynamics. Now, of course, you cannot do much with those equations because you have only one equation. You have rho and j, which are unknown. So the big assumption of hydrodynamics is that you can build a legitimate classical effective description by assuming that this flux in the right-hand side is actually a function of the density in the left-hand side. Okay, then you only have the equation for the density, which you can solve. Now, more generally, rather than working with the density, we can take some what I call useful quantities, gamma, which could be say temperature, could be velocity, could be chemical potential, and express the densities and the fluxes in terms of those useful quantities. And then you have the equations for those useful quantities that you can solve. Okay, so as an example, if your density is the density of energy, your useful quantity is the temperature, then in the left-hand side here, you have energy density as a function of temperature, which is given by the equation of state. And the constitutive relation, like this, it has to express the flux in terms of my useful quantity, which is temperature. Now, temperature is a scalar, flux is a vector. The simplest way to make a vector out of a scalar is to take the gradient. So you take gradient of temperature, and you postulate this, this relation between energy flux and the temperature, some coefficient out in front, kappa, that's the heat conductivity. And then it's easy to see that once you stick this relation and this relation into the conservation law, you get the diffusion equation. So two derivatives in the right-hand side, one time derivative in the left-hand side, that is the diffusion equation. So that's how diffusion equation shows up in hydrodynamics. So here is the summary. You have conservation laws, you have constitutive relations. You have seen that constitutive relations can have gradients, derivatives of your useful quantities, and this procedure works the same, regardless whether you work with water or quark-gluon plasma. Many different physical systems that have the same procedure for constructing hydrodynamic equations. Now, this is the theory as I outlined it for you. And as we know, every theory in physics is only approximately correct because it's limited by its domain of applicability. And whenever we write down any equations that attempt to describe physics, we have to answer these questions. Do the equations make sense? And of course, can we improve them? What kind of physics is beyond our equations? So my talk will have two parts. One part is whether the equations make sense. The second part, what kind of physics is outside of the equations. Okay, so this is the plan. So the first story is this: do equations even make sense? So you might think it's a strange question to ask. Of course they do. Hydrodynamics has been around for many decades, centuries even. But let's say you want to study relativity. You want to study relativistic fluid. Let's say you're a student in subatomic physics or astrophysics, and you want to learn about relativistic Navier-Stokes equations. Maybe you want to understand the quark-gluon plasma, or maybe you want to understand the mergers of neutron stars. So how do you study about Navier-Stokes equations? And, you know, in the early days, people read books. Okay, so I still remember those days. You would go to the library, get a book, and you read a book. So as a student, you know, I came from the Soviet School of Physics, and we had our own, so to say, Bible, the holy books of physics. And this was the 10 volumes of Landau and Lifshitz. Okay, and volume 6 is fluid mechanics, and you open it and it has some chapter on relativistic fluid mechanics, and you see some hydrodynamic equations. Okay, so then I came to the US to do my PhD. And then I realized there are other Bibles in the world besides Landau Lifshitz. And, you know, I had a copy of Gravitational Cosmology by Weinberg as a student, and it also has a section on relativistic fluid mechanics. And also there are some hydrodynamic equations. You know, and then as a student, you compare Landau, Lifshitz, and Weinberg, and like, these are different. Okay, so as a student, you're probably confused because like, what equations are you supposed to solve? However, as a student, you're also taught to shut up and calculate, not think too much, at least in some approaches. And as a simple example, we can just shut up and calculate and solve this very, very simple problem. You look at linear perturbations of the thermal equilibrium state. Okay, uniform, no flat space, no sources, just infinitesimal perturbations. Now, when you do this exercise, which you can do very easily, then you will see that both Landau-Lifshitz's and Eckart's equations, they predict two things. They predict that thermal equilibrium does not exist, or rather that the fluid is unstable. There are unstable modes, and the time scale for the instability is microscopic, not macroscopic, but microscopic. So the fluid is unstable on a ridiculously short microscopic time scale. And number two, things propagate faster than light. There are superluminal modes in those theories. So what is the problem? Okay, so the simplest case, you look at these perturbations, the plane waves, you get the dispersion relations omega as a function of k. And you have two kinds of modes when you find the frequency as a function of the wave vector, like we do in classes in electrodynamics. There are so-called gapless modes. These are the modes when frequency goes to zero as the wavelength becomes longer and longer. And these gapless modes exist because of conserved charges. They correspond to normal things that we're used to in fluid mechanics, sound waves, diffusion, whatnot. But the equations also predict that there are gapped modes. These are modes such that the frequency is finite as the wavelength becomes infinitely long. And moreover, these modes have positive imaginary port. So they give you instabilities. These modes are unphysical. These modes are outside of the validity regime of the low energy approximation. These are like high energy modes that you find in your low energy theory. So these are UV modes. So as an effective theorist, you would say, we have to throw them away. They're outside of the validity regime. We only care about low energy. But what you do in practice, you actually want to solve equations. You want to solve PDEs. You want to know that the PDEs have a well-posed initial value problem. And if you actually want to solve these equations, this unphysical mode will ruin predictability. So if you think as an effective theorist, what you would say is that you would say that cutoff scale physics messes up the infrared behavior. And the reason this happens is this happens not because if you look at amplitudes. If you look at amplitudes or correlation functions, this does not happen. But this happens because you choose to be interested in the question, which is the question of the initial value problem.
Sorry, Pavel, this happens because there are higher time derivatives in your equations. Is this right? So when you try to solve an initial value problem,
yes.
Okay, good. So if you could move the time derivatives around to space derivatives, whatever that means.
Yes, you will get equations that are not hyperbolic. You will get equations that are parabolic, like you have in non-relativistic fluids. And in relativistic systems, you want to work with hyperbolic equations. So that's.
But you can use the equations of motion to move these extra derivative terms around to make them as spatial as possible, to try to eliminate these extra modes. Does that make any sense? Yes,
it does, and you can try doing so. But the extra modes exist because you want the equations to be hyperbolic. So let me put it this way. You know from real physics, say that the modes have, say, quadratic dispersion relation, meaning, say, the frequency is related to the wave vector, like from this equation. Frequency is proportional to the square of the wave vector. Okay, yes. You know this is physics.
Yes.
And then you know that in order to have hyperbolicity, the modes must have linear dispersion relation at high wave vector. This is what is required for the equation to be hyperbolic. So you need some kind of an equation that transitions between a quadratic dispersion relation at small k to linear dispersion relation at large k. And in the process of doing, like, there is no way to just do it without introducing extra modes into the game.
Okay. Thank
you. Pavel, can I ask something? So you mentioned the two equations are different, the Landau-Lifshitz and the Eckart. For the perfect fluid, the two equations are the same, no?
Yes, that's correct.
Only because of the viscosities that the terms are different.
That's right. Yep. Right. So when I like this last point, it kind of dawned on me kind of fairly recently. Like we sort of all know this, but it's one thing to know this, and it's another thing to like internalize this. And for me, unfortunately, this happened. This last point happened sort of recently. So how is this problem fixed? So the classic textbook hydrodynamics is not what you solve in practice when you want to study quark gluon plasma. So that's not what the quark gluon people study. They don't solve equations from Landau-Lifshitz because you cannot. So you have to fix the equation somehow. And the most popular fix is this Israel-Stewart theory. And the way to understand Israel-Stewart theory from effective field theory point of view is to say we take our equations and we couple them to extra UV degrees of freedom. And this extra UV degrees of freedom conspire in such a way that the unphysical UV modes are killed. So that's what the theory does.
May I ask a question? So yep. Is this then like going along what Shiraz is saying is that there are, let us say, higher time derivatives than second order, and then you introduce auxiliary fields so that the whole system, the initial fields and the auxiliary fields are all second order, and now you have a well-defined initial value problem.
Roughly speaking, yes. Mm-hmm.
I see. So these are the additional, so to kill the unphysical modes means, okay, all right.
No. When you do this, you don't kill the unphysical modes. You still have the UV modes. But if you tune the parameters of the theory correctly, these UV modes will be well behaved. They will be stable and they will be subluminal. You can also choose the parameters of this Israel-Stewart theory in such a way that the modes will be superluminal.
I see.
So, but then if you want to solve these Israel-Stewart equations of motion, you need more data than the physical data of hydrodynamics.
Well, this is like a loaded question because what constitutes physical data? You definitely need more data than fluid velocity, temperature, and the chemical potential.
Yes, that's what I thought was like in your presentation of what hydrodynamics was, that it would suggest that was the data.
Yes. So this is like what I presented was like the most conservative approach to hydrodynamics. And in the Israel-Stewart approach, you say we have more degrees of freedom, we need more data, we need to specify initial conditions for those extra degrees of freedom.
And then the hope is that there's some attractive behavior that right. No matter what you specify for this extra data, you will flow to the same flow for the physical data. Is this right?
Yes, you're right. And I think the key word is that it's the hope. And I don't think there is a proof of that, or like convincing arguments that this will happen for generic nonlinear evolution.
Okay, thank you.
Yeah.
Actually, just one question. So here, the Israel-Stewart theory has parameters extra parameters. Is this what you want to say? In the equations, there are more parameters, or?
It has extra dynamical variables, like in the way I presented here. I said, like, my dynamical variable could be, density or temperature, velocity, but Israel-Stewart has more. I introduced some tensorial variable, which is like the dynamical stress. And for that stress, it's not just the constitutive relation that you have. That stress will be a new degree of freedom for which you write down an extra equation of motion. And that extra equation of motion will come with its own transport coefficients.
In such a way such that the whole system will be hyperbolic.
Hopefully, because the nonlinear, version of well-posedness for Israel-Stewart was proven less than a year ago. Okay, so Israel-Stewart has been around for a long time, but most things that have been proven about Israel-Stewart were proven in the linearized regime. Proving things in the nonlinear regime for Israel-Stewart is much trickier. And the fact that Israel-Stewart equations actually do admit a well-posed initial value problem, provided the coefficients in the Israel-Stewart theory obey certain stringent constraints. So that statement is less than a year old.
Okay.
So yeah, so it's a new development in a sense. And yeah, okay. So of course, the way I presented this, I said Israel-Stewart is like a UV regulator, and you can ask, can you find other regulators? Other regulators that do not introduce extra UV degrees of freedom. For example, in field theory, the Pauli-Villars introduces extra degrees of freedom, but DIMREG does not. Okay, so can you do something like DIMREG, or not DIMREG, but something that does not have extra degrees of freedom? So the claim is that it is possible to do so. So the claim is that there is a sensible relativistic hydrodynamics whose only variables are temperature, velocity, and chemical potential, just like you have in normal non-relativistic Navier-Stokes equations, and no extra UV degrees of freedom. And the catch that comes with this is that you need to choose a suitable out-of-equilibrium definition of temperature, velocity, and chemical potential. So that's the catch. So I will now comment a little bit on this claim.
Actually, one naive question here. So the perfect fluid equations are hyperbolic. That perhaps is well known or well established.
Right. So the problem with perfect fluid equations is that generally, when you evolve them in time, the the equations will develop discontinuities.
Shock waves, you mean?
Right. Yeah. Right. And
the idea is that this Israel-Stewart theory will resolve or will smoothen out the shock wave. Is that the?
Yes, that's the hope, that the viscous effects resolve shocks. That's true. Now, the Israel-Stewart theory was not, from what I understand, written down with shocks in mind. It was written down as a proposal to have a set of relativistic equations that A, include viscosity, and B, are actually relativistic. They avoid superluminal propagation and instabilities.
Okay, thanks.
So how does this work in practice? And the way I want to advocate for this is in the following way. So what we do in effective field theory is we follow these 4 steps. Step 1, identify the low energy variables. Step 2, write down all the terms that are allowed by the symmetry. Step 3, we do this up to a given dimension in the action if we have the action. So here is an example of phi to the 4 theory. And step 4, we constrain the coefficients that appear in this action so that the physics is sensible. So say this coefficient in front of phi to the 4 has to have a definite sign in order for the vacuum state to be stable. Now I say, let's do the same in hydro. So we identify the low energy variables, say temperature, velocity, chemical potential. Now this step is a non-trivial step. Okay, it's the most conservative approach to hydrodynamics, but you don't have to make this step. But you have to postulate some variables. So what I'm saying here, let's try to postulate the same variables that we are used to from our undergraduate fluid mechanics courses. Step 2, write down all possible terms in the constitutive relations that are consistent with the symmetry. Step 3, do this up to a given order, say first order in the derivative expansion. And step 4, constrain the coefficients so that the physics is sensible. So you demand that you demand stability of equilibrium, just like a normal effective field theory, you demand the stability of the vacuum. Okay. So let's see how to implement this. Okay, so this slide will be a little bit busy, so I'm sorry for this extensive notation. So if you think about the energy momentum tensor of a relativistic fluid and the charge current, say baryon number current, how you write them in terms of the useful variables. So the time component is what you identify with the charge density, and the spatial component with the spatial flux or the current, and the same for the energy momentum tensor, energy density, pressure, stress, momentum density. Now, of course, when you write down this superscript 0, this means you are in some reference frame. And in a fluid, this reference frame will be the local rest frame of the fluid. So I will assume that the notion of the local rest frame of the fluid makes sense. In other words, the states, the macroscopic states can be characterized by a time-like vector. Okay, so this time-like vector is what I will call little u. And if I want to write down these equations covariantly, I say my baryon number current or some U1 current, it has a component that is along my preferred time vector, and it has a component which is transverse to my preferred time-like vector. So this equation here, this line, is a definition of what I mean by letter capital N and what I mean by letter capital J. It's just saying this is the longitudinal component, this is the transverse component. And I can do the same for the energy momentum tensor. The decomposition is slightly more involved, but basically this script E is the fancy version of the energy density, is the script P is the covariant version of the pressure, this script Q is the covariant version of the momentum density, and the script T is the covariant version of the spatial stress. Okay, so the assumption of hydrodynamics is that all these funny script quantities, which simply is just a parameterization of the energy momentum tensor and the current, they must be written in terms of temperature, velocity, and the chemical potential. So this is something that's pretty old. Okay, so goes all the way back to Eckert, Landau, Lifshitz. Now, okay, so this slide is horrible. Okay, I actually give a class to our students in Victoria how to give talks. And I tell them, do not show slides like this. This is like too many slides, too many stuff on this slide. Don't do this. Okay, so I apologize for that. But what I want to show on this slide is this. I simply want to show that what you do is you write down every possible term consistent with Lorentz symmetry up to one derivative in your constitutive relations. So what do? So this energy density is a scalar. And there are only three scalars that you can write down. One is the time derivative of temperature, one is the divergence of the velocity, and one is the time derivative of the chemical potential. There are only three. They have to come with some coefficients, epsilon1, epsilon2, epsilon3. They're unspecified at this point. And same for pressure. There is some zeroth order contribution given by the equation of state. And there are the same three scalars that you write down with arbitrary coefficients. Time derivative of temperature, divergence of the velocity, time derivative of the chemical potential. And again, these coefficients by 1, by 2, by 3, at this point unspecified. You do the same for the energy flux. Write down three transverse vectors, acceleration, gradient of temperature, gradient of the chemical potential. They have to come with some arbitrary coefficient unspecified at this point. The transverse traceless part of the stress tensor has to come with the shear tensor. This is some symmetrized trace subtracted derivative of the fluid velocity. The coefficient here is the viscosity. And you do the same for the charge density, three scalars, and for the charge current, the flux, with the three transverse vectors. So you count them and you say, okay, there are 16 one derivative parameters. There are too many. But what I want to do now, I want to talk about so-called frames. So in hydrodynamics, As I learned from papers by Shiraz and co-authors, frame simply means a convention for how you choose to define temperature, velocity, and the chemical potential beyond perfect fluids. So I'll let you read this cartoon for a second. That's about temperature. Okay, so it tells you how you measure temperature. How you measure temperature is important. So temperature, as we teach our students in thermal physics, temperature is something that is only unambiguously defined in equilibrium. So by definition, temperature is the quantity that is measured by a thermometer. Now, here's an example. So I have two boxes. They have yellow stuff or orange stuff in equilibrium. These are two identical equilibrium states. And what I have here, I have inserted two different thermometers in my boxes, the green thermometer and the red thermometer. These are little heat reservoirs of the thermometers. They're connected to the gauges. And if the thermometers are properly calibrated, then in identical equilibrium states, these two different but properly calibrated thermometers show the same temperature. Okay, this is clear. Temperature is well defined in equilibrium. But let me now do this thing. Let me take the same two thermometers and stick them in identical non-equilibrium states. Okay, so these two boxes now contain identical non-equilibrium states. Now these two thermometers will show different temperatures, even though they showed the same temperature in equilibrium. So why is this? So we know this from our real experience. If you have two different thermometers outside of our window and say one of them takes longer time to adjust to the outside temperature changes, if the temperature drops very quickly or rises very quickly, then the thermometer will not adjust. And yeah, they will show, two thermometers can show different temperatures. By the way, can you see my screen all right? Yeah? Yeah, it's great. Yes. It's great, yeah, okay, good. Something is happening with my screen here. Okay, good. So what I want to argue is that these measurements given by two different thermometers, they can be interpreted as temperature in two different quote-unquote frames. So this is the physical meaning of a frame. This is temperature measured by two different thermometers. So frame is a definition of temperature, velocity, chemical potential beyond zero derivative order. So frame means convention. So change of frame is just a field redefinition of temperature, velocity, chemical potential by derivative corrections. And because we always work with some temperature, velocity, chemical potential, we always use some frame. So it's impossible, so to say, not to choose a frame. So temperature, energy, momentum, tensor, and the current, they don't care which frame we choose to use. They're the same in all frames up to a given order in the derivative expansion. This is again something that I learned from older paper by Shiraz and collaborators. Now, but I want to kind of expand on that. So the moment we write down constitutive relations with some specified values of these funny parameters, of these many parameters, these constitutive relations will define for me a certain frame. So, of course, there is no such thing as the Navier-Stokes equations until we specify our arbitrarily chosen conventions. So in the Landau frame, the convention is such that all these terms that are crossed out, Landau-Lifshitz set them to zero using field redefinitions and on-shell relations. And the terms that you keep is the blue, which is the perfect fluid, and this pi2, which you interpret as the bulk viscosity, eta is the shear viscosity, gamma 3 is the charge conductivity. Eckert frame does something else. So Eckert chose a different convention. He said, let's throw away all the terms except for this pi2 with the shear viscosity, this theta1 and theta2, which now will be interpreted as the charge conductivity, and this eta, which is the shear viscosity, and all these things will be thrown away using the field redefinitions and on-shell relations. Now, the fact that you can push most of these one derivative terms to higher order doesn't mean that you have to. Okay, doesn't mean that you have to. Let's skip all of them for now. Let's use the most general frame. So does it matter which frame you use? So the choice of frame is not important at all from the point of view of the derivative expansion, if you want to classify transport coefficients, but it is important from the point of view of the hydro equations themselves. And this is because the hydrodynamic equations, with their constitutive relations truncated at one derivative order, when you write them in different frames, they give rise to different partial differential equations. Okay, so the choice of frame may potentially affect such things as well-posedness of the initial value problem for these partial differential equations, or it can lead to fictitious instabilities of the equilibrium state. And this is coming back to the problem that the choice of frame, if you're an effective theorist who is interested in computing amplitudes or correlation functions, you don't care for this. But if you want to solve the initial value problem, then you must care for this. So the main claim is that in this space of all these many transport coefficients, there is a subspace where hydrodynamics is stable and causal. So some of these coefficients, it's necessary to keep them non-zero positive unbounded from below. So these coefficients, I view them as some kind of regulators. But the claim is if you analyze the equations in the most general possible frame, you analyze the equations for well-posedness, then there exists a subspace in the space of all those coefficients. And the frames of Landau, Lifshitz, and Eckert, they fall outside of that stable and causal subspace. Now, what are these coefficients? So at one derivative order, there are all these coefficients. Epsilon spi's, there are a total of 16 for charged fluids with non-zero chemical potential. If you demand that the choice of frame is consistent with extensivity in equilibrium, this is again demanding it's consistent with the energy momentum tensor that comes from the hydrostatic partition function. Again, as was first explored by Shiraz and collaborators, you reduce that down to 14. So out of these 14 parameters, 3 combinations will be genuine transport coefficients, which is the shear viscosity, bulk viscosity, and the conductivity. So you have 14 minus 3, 11, one derivative quote-unquote transport parameters, which are not physical transport coefficients. You can eliminate them by choosing a frame and using on-shell relations. So these 11 parameters, they have no Kubo formulas. They no fundamental microscopic definitions. You cannot compute them from ADS-CFT, and you cannot fix them if you go to higher order in the derivative expansion. So these are like regulators, UV regulators. So they are regulators which make the UV of hydro consistent with relativity. So these parameters ensure that the gapped modes are in the lower complex half plane, just like they are in the Israel-Stewart theory. And by the way, in the Israel-Stewart theory, you also have to choose, certain values for those parameters for that consistency to happen. Most of these parameters can be set to 0 without sacrificing stability and causality. So I said, there are 14, that's too many. You can set most of them to 0, doesn't do anything. If you like kinetic theory, in kinetic theory, these extra parameters appear as integration constants that parameterize 0 modes of the collision operator. So when you solve Boltzmann equation, there are some integration, not integration constants, but like integration functions, free functions that appear because of the 0 modes of the collision operator. And these free functions is precisely what gives rise to to those extra kind of parameters that you can think of as the UV regulators. Now, if you think of Israel-Stewart as a Pauli-Villars regularization, think of these frames as a high derivative regularization, except the regulator formula appears at the same order as viscosity. So just to give a very simple example for how this works for conformal fluids. So for conformal fluids, the pressure is fixed by scale invariance, temperature to the force, some function of chemical potential over temperature, some relations among those parameters that you have with a factor of 3 because of 3 space dimensions. And the simplest possible frame says, set all of these extra guys to 0, take 3 of them to be non-zero, to be bounded from below by these inequalities. They have to be greater than 4 times the viscosity. This one has to be greater than temperature times conductivity plus, something. N is the charge density, energy density, pressure. And if these inequalities are satisfied, you're guaranteed to have well-posed Navier-Stokes equations for conformal fluids, which do not involve introducing any of the extra variables like you do in the Israel-Stewart theory. So the reason I'm showing this slide is because you see these inequalities are quite simple. You know, some coefficient has to be greater than 4 times the viscosity. It's very easy to implement in practice. So the bottom line is this. So choose a physically sensible thermometer or velocimeter, and then the Navier-Stokes equations happily unified with relativity. There is no need for extra UV degrees of freedom. So now this is an old slide because I've shown this slide before. Now on this slide, I said, now we need to develop numerical codes and apply them to actual physical systems. Well, guess what? Last week, you know, Franz Pretorius and, you know, his students, so they have this paper, a numerical exploration of first order relativistic hydrodynamics, you know, doing exactly that. Though they say, let's take these equations in some stable and causal frame and develop a numerical procedure to solve them and compare the results with Israel-Stewart. And they say that, you know, there is, you know, still some work to be done, but it looks like it has, in some sense, it works better than Israel-Stewart in terms of resolving shocks. Okay, so this paper came out on, well, it was submitted on April 1st. I hope it's not a joke, but it appeared on the archive a bit later. So yeah, I'm quite excited. I'm still like trying to read through like everything that that they did here, but you know, all I want to say that people are looking at these things. So, however, this whole thing leaves us, well, with this philosophical question, which I think is slightly troublesome. And the question is this: sensible relativistic hydrodynamics seems to require that its equations contain non-hydrodynamic parameters. This is true in the Israel-Stewart theory. This is true in this, you know, funny frames. Your equations need to have this, you know, quote unquote UV regulators. Now, if the equations in order to be well posed need to depend on these non-hydrodynamic parameters, like the parameters of your thermometer, this means that the solutions to your equations will depend on those parameters. Now, if these parameters are really UV regulators, so what you do, you solve the equation and the solution depends on the UV regulator. So what you want to do, you want to ensure that the physical answers that you obtain are independent on the UV regulator. Now, how to do this in practice? I don't know. Maybe some people who are more mathematically minded than myself, maybe somebody has thought about this. And you know, I'm sure in the context of simpler PDEs, people have. But this is something that, you know, I don't know how to do. I don't know how to do, you know, renormalization group, so to say, for these partial differential equations to ensure that the predictions are independent on the UV regulator parameters. So how do we know that, you know, there is some predictive power? And so what people do in practice, it's very kind of simple. They say, okay, we have some, say, Israel-Stewart, and there is some UV regulator parameter that the equations have. People say, okay, let's solve these equations and, you know, find some solution. And let's change this parameter by a factor of 2, and let's solve the equation, and here is another solution. You know, and if the solution changes by like 10%, well, maybe it's good enough. So it's sort of.
Yeah, can I ask a question? So,
yeah.
So in terms of an analogy with field theory, so so you can impose RG invariance, beta functions, and so on, so that your physical quantities are independent of the, let's say, lattice cutoff or some parameters like that, which are extraneous to your problem. And so, and then there is the another issue is of independence with respect to RG schemes. So, for example, what you can show is that your S matrix, okay, is that kind of a physical quantity which will be independent of what RG scheme that you have used. So so these are two independent issues. Staying within a particular RG scheme, you can demand, invariance with respect to the cutoff, and you will get some physical things. And then, however, your questions can also be, you can have questions which are independent of even the RG scheme. So are there analogs of both of these things in your analysis?
Well, yeah. So the issue of RG scheme, I'm not even sure how to think about it.
So this frame, the choice of frames, isn't that like RG scheme? Or maybe I'm not.
It's sort of, it's sort of like choosing different cutoffs. Maybe you can phrase it as RG scheme, but it's like using it's like real space cutoff versus momentum space cutoff. Not exactly. It's not exactly the same analogy. It's more, I think a better analogy in field theory is you throw in literally some high derivative terms. You add high derivative terms in the Lagrangian that will, regulate, some UV divergences and loops. And there's a freedom of what kind of high derivative terms you add. Let's say we choose to add, certain kinds of high derivative terms, and let's say this is the kind that we like. And then the question is how to ensure that in this case, the solution to the initial value problem will be independent, on the coefficients of those high derivative terms.
Yes.
Sorry. One more question, please, Pavel. In your first order hydrodynamics, what is the data you need to specify the solution? Is it the temperature and, ignoring charge density for a moment, is it the temperature and velocity and its first time derivatives?
That's right. That's correct. You need the first time derivative. It's a hyperbolic equation. It's like the wave equation. You need to specify the first time derivative. That's right.
So that's another issue, right? So it's double the data that you would naively think is physical, and you would want some sort of flow in this data space.
Yeah.
Well, it sort of depends what, let's say, what is the data that we need to specify the initial to specify the further evolution of a fluid? So is it just the energy momentum tensor, or is it something else? So say what the Israel-Stewart theory says. Israel-Stewart theory says you have these extra parameters, but you can fix those extra parameters just from the energy momentum tensor at a given time. You don't need time derivatives. Now, but what this scheme cannot say, it cannot say the following. So suppose you have two energy momentum tensors, and both of them are the same at time is equal to 0. But one physical state has huge time gradients, and the other physical state has very small time gradients. In the Israel-Stewart theory, there is no way to distinguish the two as far as the initial value problem goes, because the only thing that goes there is the value of the energy momentum tensor at a single moment in time. Okay, so if something changes very rapidly afterwards or something changes very slowly, Israel-Stewart does not know this. Now, in this approach, you have some control of that. That is, you can demand that the initial time derivative stays within the domain of validity of the hydrodynamic theory. And you can do this very easily in practice, because very easily in practice, what you can do, you can say, reconstruct the velocity, fluid velocity in the Landau frame. And this you know how to do from the value of the energy. The Landau frame velocity is just the eigenvector of the energy momentum tensor at some fixed moment of time. Now, once you know the velocity in the Landau frame, just perform a frame transformation to find the velocity in some other frame. And the frame transformation will involve the time derivative, but so what? You know, that's. Oh, you're muted, I think.
Shiraz,
Your mic is muted.
Sorry, just to understand. You take your equations and you linearize them. Then you have some soft modes, meaning modes whose omega goes to 0 as k goes to 0. And you've got some heavy modes, namely modes whose omega goes to some fixed number as k goes to 0, something fixed by the temperature, let's say. Okay. Now, naively, one would have expected that the dynamics of the soft modes is somehow independent of what the hard modes are doing. So it seems to me that you're raising the possibility that that's not true, that to really understand the late time, long wavelength evolution of the soft modes, it's important that you are able to specify the data for the hard modes, for your hard modes, the ones that are the doubling modes. And that changing this data will change the late time dynamics of the soft modes. Is this what you're suggesting? That sounds weird to me, if that's what you're suggesting.
Yeah, I'm not. So it's maybe. I agree. I agree. It sounds weird. I completely agree that it sounds weird. However, it may be that this is what is happening simply because we're required, or so we are demanding that we have a classical theory that is hyperbolic. Okay, because hyperbolicity is something that is needed in order for consistency with relativity, right? So if something is not hyperbolic, there is no chance you can couple it to Einstein's equations, for example, right? So now, and because now we have hyperbolicity, now for hyperbolic equations, you must specify, the first time derivative. That is what has to happen, right?
Right, but wouldn't the most satisfying situation be that to get a hyperbolic equation, you need to specify also the first time derivative, but that's some sort of attractive flow, so that you wait long enough in units of the temperature, and then what the soft modes are doing, that there's an equivalence class of initial conditions such that all of them lead to the same low energy behavior.
Yes, I would very much love that to happen, and so this is one question, for example, that was explored in this paper. And they say that for the initial conditions that they have studied, this is what seems to happen. Even if you start with the initial conditions, which are maybe outside of the validity regime or close to the being on the borderline validity regime of hydro, after a short while, this UV physics dies out, and you are still and you are flowing, so to say, to the kind of regime with small gradients.
Right. So you could hope to prove some sort of dynamical Boltzmann H theorem that says something like this, right? That there's some.
That would be wonderful. Yes.
Okay. Thank you.
Yeah. But also on the other hand, if you look at the dynamics of an actual fluid, like you go to the seashore, right? And what you see that waves break. So like, how does a wave break? Right, so wave, when it's far out at sea, it starts with very, very long wavelengths. Now it comes closer to the shore, it breaks, and you get, this foam and splashes and all kinds of stuff, which is technically supposed to be outside of the validity regime of hydro, because you're developing, what looks like infinite gradients, or maybe gradients that are resolved at the viscous scale. So it's not,
I see. And suppose this second possibility is realized, then it looks like if you choose different of your UV cutoff parameters, different values for your parameters, you will just get genuinely different dynamics.
I would be horrified if that is the case. And in this example that, for example, Franz and Alex looked at, this does not seem to be the case. Of course,
the simplest way it would not be the case is this universality for the low energy modes.
That's right.
Yes. Okay. Thank you. Sorry for interrupting.
That's right. Yeah. And as somebody just pointed out to me, it's maybe another way to think about this is that the invariance of late time physics under frame transformations. So that is, you know,
Right.
So if that is the case, then great, we're in business. And
if it's not the case, it sounds worryingly close to me to saying that there is no theory of with just the UV degrees of freedom. Sorry, IR degrees of freedom.
Yes, and yeah, I would, you know, I would be sad if that is the case. But I want to say is that it's not obviously clear that that is not the case.
Okay, thank you. Yes, I agree. Okay, but it would be, I would also be sad if that was not the case.
Yeah.
Okay. Okay. Sorry,
yeah.
but I'm interrupting you too much. Sorry for that.
Actually, I have two questions.
So
Short questions, if you can.
Yep.
So is the Israel-Stubble theory part of this 16 parameter space, or is it outside this 16 parameter space?
no, it's a different theory. It's a different theory because it has other dynamical fields. So this parameter space that I'm talking about is within the theory whose only fields are like what we are used to, you know, temperature, fluid velocity, chemical potential. And these are the fields, only the variables that you solve for. In the Israel-Stewart theory, there are other variables that you have to solve for, and for which you have to specify the initial conditions.
Okay, and one other question. So in the context of fluid gravity correspondence, do you think it is possible to get all these 16 parameters?
Yes, of course. And this is because there are, like, if you look at fluid gravity, I mean, I'm not the one to talk about fluid gravity here, of course, but if you look, you know, there is a freedom. There's a freedom of choosing the frame that exists at a certain point in the procedure. And the simplest way of fixing the frame is to choose the Landau frame, but you don't have to do this. You can choose another frame which is not the Landau frame. It's it's a choice. So how late do your seminars run?
Pavel, we're very, you know, since you're a Russian speaker from the Russian school, we'll go with your tradition. You know, we are very flexible. So
well, I mean, I know normally people have, you know, meetings, maybe classes, maybe other things. So if you tell me, please finish by, you know, point X, then I will finish by point X.
Well, you know, it's very rare that our speaker goes on for less than 1.5 hours. And if you need more, we are happy with that. So please just, it's going fantastically. Don't just go at the speed you'd like.
Okay. Thank you. So the second question that I want to talk about are things beyond classical hydrodynamics. So as I outlined, classical hydrodynamics is basically conservation laws. And here are some equations with, you know, you have more equations, more unknowns than you have equations. And you introduce some what I call useful variables or proxy functions. Beta would be like the fluid velocity, or maybe fluid velocity divided by temperature. Alpha is like chemical potential, maybe chemical potential over temperature. So this is some constitutive relations that we stick into the conservation laws. Okay, so conservation laws, then constitutive relations. Now, if we assume locality and small gradient, we can write down some kind of derivative expansion for these constitutive relations in terms of my chosen fluid variables, like the fluid velocity, chemical potential, temperature, whatnot. This is basically just repeating what I already said before. But now I want to do something like take one step further. I want to look at very simple solutions of classical hydrodynamics, meaning how the near equilibrium physical system relates to infinitesimal external sources. Okay, so I want to take my constitutive relations and I want to throw in external metric G and external gauge field capital A. Okay, so now my constitutive relations depend on beta, which is like fluid velocity, temperature, chemical potential, external metric, external gauge field. Now, when we solve the conservation equations, solve the hydrodynamic equations, we find our hydrodynamic variables like temperature, velocity, as functionals of the external sources, the metric and the gauge field. Okay. Then we take these things, we stick them back into the energy momentum tensor and the current. And what we have the hydrodynamic predictions of how the energy momentum tensor and the current react to external sources.
So, and the initial condition is that it's in equilibrium to start with?
Yes.
Thank you.
Or the initial condition, we also say, we can take the initial condition the same as in the linear response theory, that at some time minus infinity, we slowly try to turn in those external sources, and we evolve them at time is equal to 0, and then starting time is equal to 0, we see how the system responds.
Okay, thank you.
Right. So yeah, but this is, yes, this is supposed to be infinitesimally close to thermal equilibrium. So once we have these relations, how the energy momentum tensor and the current react to external sources. So this is a prediction of the classical hydrodynamic effective theory. We then expand to linear order in the sources. So there's zeroth order term, and there is the first order term, proportional to the metric, proportional to the gauge field. Now these coefficients of the first order terms are, of course, the correlation functions, the retarded correlation functions. This is what the linear response theory says, that these things, the coefficients of how the energy momentum tensor and the current respond to the sources, are the retarded functions. Okay, so classical hydrodynamics gives predictions for retarded functions of conserved densities and fluxes energy momentum tensor in equilibrium. So for example, this is the retarded function of charge density, Fourier transform as a function of frequency and the wave vector. You see the G is the diffusion constant. There is a singularity corresponding to diffusion in the denominator, something in the numerator. Or you can do similar thing with the stress, xy, some pressure here, some viscosity here, and so on. Now, these correlation functions do not depend on which version of hydrodynamics one is using. These are universal predictions of classical hydrodynamics for observables. So these formulas give rise to Kubo formulas for viscosities, whatnot. So this is something that people have, known how to do since the time of Kubo, many decades ago. Now, question: are these predictions of classical hydrodynamics actually correct? This kind of classical predictions with normal singularities, normal things that you get from solving equations. After all, classical hydrodynamics, meaning when you think of hydrodynamics as partial differential equations, is just a toy model of fluids, and nature may or may not care for our toy models. Okay, so let's look at limitations of hydrodynamics. So the limitation of hydrodynamics that I want to focus on here is this. Macroscopic stuff is made out of microscopic stuff. Okay, so in a quantum vacuum, virtual particles constantly produced and absorbed due to quantum fluctuations. Similarly, in a macroscopic state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. These sound waves will back react on the macroscopic physics because hydrodynamics is nonlinear and waves interact. So here's a cartoon that I have the profile of temperature or the velocity as a function of distance. So the thick line is what you think your hydrodynamics does. The thick line is what you get from solving classical partial differential equations of hydro. And this is a cartoon of a statistical fluctuations that emits sound waves. And these thin statistically generated sound waves will interact with the big sound wave because, of the nonlinearities in the equations. So these effects exist. So what do these effects lead to? So the claim that was made in late 60s and early 70s is this: even if you're interested in macroscopic long distance response near static equilibrium, then classical hydrodynamic equations, which ignore the back reaction, they can lead to predictions that are qualitatively wrong, not just quantitatively, but qualitatively. So this paper is one of the early papers from the early days of molecular dynamics. People just said, hey, let's take billiard balls, or if we're in two-dimensional, like rigid disks, let's take a whole bunch of them, give them some energy, and look at their macroscopic behavior. Does the behavior follow Navier-Stokes or not? And in particular, are these things true? Turns out it's not. And the rest of the talk will be comments on this claim.
So a quick question. The worry that you have would go away in a large n, at leading order in large n? Are these 1 over n
right.
suppressed things? Yes.
That's right, yes.
Okay, thank you. Sorry, and one more similar question. You might think that these things, because their statistical fluctuations, are less and less important at longer scales because of 1 over square root n fluctuations, where square root n is the number of molecules contained in that box. Yes. And this, you say, is too naive.
It's not too naive. They will be less important at longer scales, and the effects of these fluctuations will be derivative suppressed. However, how suppressed they are in the derivative expansion, this will depend on the, say, number of space dimensions.
Right. So
for example, in 3 dimensions, the simplest quantities that you can look at, you can say even Navier-Stokes is good. But in 2 dimensions, you can say, well, maybe Navier-Stokes is not good. It's only perfect fluid is good. And if you go to 1 dimension, then, it's even more important. Maybe perfect fluid is not good at all.
So this 1 over square root n fluctuation would naively say 1 over L to the power p by 2, where p is the number of space dimensions. Right, so 1 over L to the 3 by 2 in three space dimensions, or 1 over L in 2 space dimensions. Is this roughly anywhere near the truth?
Sort of, except it's not just the physics of space here, it's also the physics of time. So these fluctuations will not do anything interesting if you are in the Euclidean theory and if you're asking Euclidean questions. But if you are asking specifically questions about real-time correlation, so you want to specifically ask about the scaling of frequency rather than the scaling of wave vector, or rather the relationship between the two. So it's really literally the real-time physics that is at play here.
Thank you.
So here is a cartoon of viscosity in a gas. So viscosity is basically something that tells you about momentum transfer between different layers of fluid. So what I have here on the left is a fluid that moves from right to left. So the thick yellow arrows is the macroscopic flow of the fluid from right to left. Now, these thin blue lines, they represent particles that jump between layers of fluid. And what you see here is that if this particle here jumps from this layer at the bottom that is moving fast to this layer at top that is moving slow, it can speed up the top layer. Okay, so basically what this will tell you is that in a gas, the viscosity will be proportional to the mean distance which is traveled by these particles. And if you convert this to hydrodynamics, you can also relate this to correlations of stress. So this is a pressure which comes from perfect fluids. There is 1 derivative, 1 power of frequency that comes from Navier-Stokes. And then there are omega squared that comes from 2nd order hydrodynamics and so on. Now, on the other hand, momentum can also be transferred by collective excitations. So it's the same picture now as I had before, except instead of thin blue arrows, I have these thin wiggly lines. And these wiggly lines, I can think of sound waves that are generated by statistical fluctuations. Now, in a gas of sound waves are, the mean free path is inversely proportional to k squared. Long wavelengths propagate longer because dissipation is less at long wavelengths. And they're also inversely proportional to the viscosity because, the less the viscosity, the longer they propagate. Now, if you now look at the contribution of this gas of sound waves to viscosity, so what you have to do, well, okay, it depends on K. So we have to sum over all possible values of K to find the contribution to the viscosity. So T here is just for dimensional reasons, just ignore it. But you have 1 over the viscosity and K squared, and you have to integrate over D, dk, capital D is number of space dimensions. And what you see, if you want 3 space dimensions, there's going to be some UV cutoff, and the integral is going to be inversely proportional to eta over S. And so what this will tell you is that small viscosity means large fluctuation corrections to viscosity. But if you're in 2 space dimensions, then you see that this integral is actually divergent in the infrared. And infrared divergence means there is some infrared physics that we are not maybe properly taken into account. So this is this physics of statistical fluctuations. It is invisible if hydrodynamics is viewed just a collection of partial differential equations. And also based on this argument, if you think that the viscosity can be arbitrarily small, well, think again, because if you try to make viscosity arbitrarily small, then the corrections to viscosity will become very large. And also what this tells you is that classical hydrodynamics may be questionable in two space dimensions once you start asking questions about, Kubo formulas, long distance limit, and whatnot. So how does one describe these effects quantitatively? So the simplest way how people started describing these effects quantitatively is through so-called stochastic hydrodynamics.
Sorry, Pavel, quick question. If you were interested in a second order transport coefficient,
yep,
would the contribution to that become sort of divergent or more important due to these fluctuations, even in four dimensions? Even
3 plus 1, in 3 plus 1, yes.
Yes. Okay, right. That's what this 1 over L to the power P by 2 would suggest. Because 1 over L to the P by 2 is 1 over L in 2 dimensions, which is same order as viscosity. Whereas 1 over L to the 3 by 2 is higher order than 1 over L squared. So it sounds like it should be very contributing to the second order. So, right.
Yes.
Okay, thank you.
Yes. So the simplest way how people have started describing these effects is a sort of phenomenological description that goes back to Landau and Lifshitz, and before that to Langevin. It's basically how do you describe Brownian motion using the Langevin equation. So what you say is okay, we have the energy momentum tensor has the classical part that is given by the constitutive relations. This is like the friction force in the Langevin equation. And then you add some random noise, okay? Just like you do in the Langevin equation. And when you look at correlation functions, you have to average over the noise, and you average over the noise with some weight. So you perform a path integral over that noise that now appears on the right-hand side of the energy momentum tensor in the current. You perform path integral with some weight. Okay, so this action for the noise is Gaussian for long wavelength fluctuations, essentially by the central limit theorem. That is because the small parameter here is the correlation length divided, or correlation length times the wave vector. So the width of this Gaussian action is determined by demanding that the equilibrium two-point correlation function satisfies the fluctuation dissipation theorem. So fluctuation dissipation theorem is a statement that's symmetric function and then is related to the imaginary part of the retarded function. So you can use that to fix the coefficient of the quadratic Gaussian term in here. And this, I think, is described even in Landau-Lifshitz statistical physics part 2. Or it's Lifshitz and Pitaevsky. So the way you kind of tie this with these cartoonish pictures that I gave earlier is that if you think about the energy momentum tensor, okay, it has some linear piece, which you can think about giving you the propagators of the theory. It has some interaction piece that comes from non-linearities, and this particular interaction piece is just fixed by boost covariance here. It has high orders and derivatives and non-linearities, and it has the noise. Now, if you look at the tree-level propagator that comes from this linear term, it gives you what you naively think is the viscosity. So this gives this cartoonish picture on the left. And if you now look at the loop diagram that comes about by joining two legs at each vertex like this you can identify with this effect of statistically generated sound waves. So this is a very, very kind of simple picture. But in the next few minutes, I'm going to make it more advanced, so to say. So what happens when you do this? What happens when you look at this one loop diagram? Okay, so what happens is this. So this is the two-point function of stress retarded function at zero spatial momentum. So the terms that are highlighted in red are the terms that come from classical hydrodynamics, meaning hydrodynamics as partial differential equations. There's zeroth order, which is the pressure. There's first order, Navier-Stokes, the viscosity. Then there's second order, some second order hydrodynamic terms with omega squared. Again, this is for zero wave vector. There is no k. Now, the terms that are in purple are corrections that from that one loop diagram. There is going to be some correction to pressure that is dependent on the UV cutoff. And this is the UV cutoff of the effective theory that is determined by maybe the interparticle distance. Then there is a correction to viscosity with a well-defined coefficient. It's inversely proportional to the viscosity, as you expect. The coefficient, again, depends on the cutoff. But then there is a term which goes as omega to the 3/2. Okay, now this term does not depend on the cutoff. There is no dependence on the cutoff. It's inversely proportional to viscosity to the 3/2. And what you see is that this term is more important than omega squared. So it is less important than Navier-Stokes, because Navier-Stokes comes with omega, but it is more important than second order hydro, which comes with omega squared. And this contribution is just determined by thermodynamics and the viscosity. Now, in real time, this omega to the 3/2 gives rise to a power law decay of correlations, 1/t to the power 3/2. And this is what people call long time tails. This is actually more important than first order hydro, because if you wait long enough, then in real space, in real time, this will decay exponentially, and this will decay as a power law. And at late times, power law wins. Okay. In 2 + 1 dimensions, this omega to the 3/2 will give you a logarithm. And what this tells you is that if you now try to think about the Kubo formula for viscosity, it will not exist because this logarithm blows up at zero frequency. Now, another way to put those comments that Shiraz made is that the large n limit does not commute with the hydrodynamic limit. Hence, this omega to the 3/2, this thing is not visible in classical holography. It will be visible if you include loops in the bulk, but classical, it is not visible. So this is a simple analogy with quantum gravity that maybe some people are familiar with. And the analogy goes as this. If you look at hydrodynamics, you look at perfect fluids, you look at Navier-Stokes fluids, and second order fluids. So for these correlation functions of stress in this example, the perfect fluids give you something that's order 1. Navier-Stokes gives you one more derivative, order omega. Second order fluids give you 2 derivatives, omega squared. But there is also the statistical fluctuation piece that gives omega to the 3/2. That is, in this 3 + 1 dimensions, less important than Navier-Stokes, more important than second order. If you now look at what happens in perturbatively quantized quantum gravity around flat space, this is the Einstein-Hilbert term, and you can write down possibly high derivative terms. And then you can ask the question, what does the two-particle potential look like based on that action? So that was actually, classically, it goes back to Stelly in late 70s from high derivatives. But quantum mechanically, it has been worked out not that long ago, but by Bjorn Bohr, Donahue, and Holstein. And what turns out is that if you look at classical gravity, then you will have this normal Newtonian piece. You will get some corrections from GR. You will get some exponentially suppressed piece, suppressed by the mass scale that suppresses these high derivative terms. But if you look at the graviton loop that was worked out in this paper, actually a series of papers, then it turns out that the loop is gives you a power law. So in this example, it's a power law, but it has an H bar. So this is an example when the quantum correction is more important than the classical higher order correction if you ask the question about the interparticle potential. Okay, sort of kind of analogously to what happens here with hydro. And of course, this is the physics of massless degrees of freedom in loops. So massless degrees of freedom in loops give rise to infrared effect. So gravitons in loops give you this thing. Sound waves in loops give you this thing. Okay, so bottom line is this. So using classical hydrodynamics to evaluate this small omega, small k sources is unreliable. Evaluate the response to these sources is unreliable. Short time statistical fluctuations give rise to infrared late time correlations, and deviations from classical hydro are more pronounced as small viscosity. Okay, so the effects that I talked about from this stochastic hydrodynamics, there is a prediction that these infrared correlations, they're universal. They're determined by thermodynamics and transport coefficients. These are like these kinds of effects. You can I don't write down what the number is here, but you can write down the numbers, just some pi's and 2's and roots of 2's and whatnot. But the problem of classical hydro don't end here, especially if you want to do high derivative hydro. Let's say you want to go beyond normal one derivative hydro. Then you realize this. The noise is only Gaussian as k goes to 0. But what if you want to do the derivative expansion beyond the leading order? This means you're probably looking at noise that is not Gaussian. How do you know what the noise is? Now, what I also said is that the width of the Gaussian was fixed by the fluctuation dissipation theorem for 2-point functions. But fluctuation dissipation theorem exists for all endpoint functions, not just for 2-point functions. So how do we impose those fluctuation dissipation theorems for endpoint functions? Another thing is that classical hydro can only compute retarded functions. You take the variation with respect to the source, you only get one type of function, it's the retarded one. But non-retarded one are invisible to classical hydro. Well, they're invisible to classical hydro, but they contain new information. Okay, so they are not related to retarded function by the fluctuation dissipation theorem, but they contain new low energy information. So how do you access that new low energy information, which is potentially measurable, but it's not fixed by the classical Navier-Stokes equations to any order in the derivative expansion? Okay, so these are the questions that you have to ask, that if you want to go to higher order than naive first order Navier-Stokes in the derivative expansion, or maybe go beyond perfect fluids in 2 spatial dimensions, you have to think about the effects of the statistical fluctuations much more carefully. So the answer that has emerged recently is this effective field theory. Okay. So normally the way we are used to do things in effective field theory, okay, so we again identify low energy degrees of freedom, identify the symmetries, write down a local action that is a function of the symmetries and the degrees of freedom and external sources that is invariant under those symmetries. You get the correlation function by writing down some kind of path integral like this, integrate over the fields. Action depends on the fields and the sources. So this is what we kind of are used to from effective field theory. So question, can you do the same for non-equilibrium states? Okay, now in such an effective field theory, classical hydro equations will be like the classical Euler-Lagrange equations of motion. And stochastic hydrodynamics will emerge as a leading Euler truncation of that effective theory. Okay, so things like that have been explored by people in the last 5 years or so. So this is not my work. I mean, the earliest thing actually goes back to 1970s by Martin Singer-Rose. Lately, in the last 5 years, there are especially the three groups, Liu, Honglu, Crossley Gloriosa, also Rangamani, Lognaigam, and Hell, and also Jensen, Pinzani-Fekete, and Jerome. They have been, pursuing this this program of developing actual, like Wilsonian effective field theory in mixed states, where time is important. So it's essentially non-Euclidean. Okay, so you impose all the normal things: locality, gauging, diffeomorphism, and variance. You want the Euler-Lagrange equations of motion to be the conservation laws. Okay, so this is different from what we normally teach our students. Normally, when we teach classical mechanics, we say, oh, there is classical equations of motion, and then they imply conservation laws. But here we want something else. We want the equations of motion to be the conservation laws, like this. You want to access real-time correlation functions. Therefore, you need to formulate the effective field theory using Schwininger-Keldysh fields, which means you need at least 2 copies of all the degrees of freedom and the sources. And if you're in equilibrium, you want to impose a Kubo-Martin-Schwininger constraint as a symmetry of the effective action. So this is also a new ingredient. Okay, so I have some slides about the development of this effective theory, but I'm coming to the end of my 1.5 hours. I'm actually running out of my voice myself. So I will maybe skip the constructs that go into the development, into the formulation of this effective theory. What I will say is that all I was going to be talking about here is from this paper by Honglu and his students. And you can write down this theory based on the right fields that do all the things that you want. You can see how stochastic hydrodynamics emerges from that effective field theory. The effective field theory will have not just the normal hydrodynamic fields, it will have an extra type of field, which is this, I call this the A type of field. It's not the normal fluid velocity, it's this an extra degree of freedom that is associated with statistical fluctuations. Now, the thing that I want to comment about here is this. So the physics of diffusion that I talked about earlier at the very beginning of the talk, it can be captured both using this formalism, both the classical diffusion that comes, so this is the diffusion equation here in parentheses, sigma is the charge conductivity, mu is the chemical potential, n is the charge density. So what you see here, if you just ignore the quadratic term and integrate out the phi field, you get the classical diffusion equation as a constraint. And there is this, here is the Gaussian noise with some coefficient. And this coefficient here for the Gaussian noise, it will relate, it will be related to the diffusion constant or the conductivity through the fluctuation dissipation theorem. Now, this Gaussian noise has 2 pieces. One piece that has this delta, and another piece that has this other thing. So this other thing in the square brackets, it contributes to the 4-point non-retarded function. And this 4-point non-retarded function is not related to retarded functions by the fluctuation dissipation theorem. And so what this tells you the following. It tells you, once you write down all these terms in the effective theory, you realize that there are going to be terms here that are actually Gaussian, but which are invisible to the fluctuation dissipation theorem at the level of 2-point functions. Okay, they're invisible to classical hydrodynamics. So this coefficient that sits here, it's a coefficient in the effective field theory. And in terms of transport coefficients, you can call it a stochastic transport coefficients. It is possible for this coefficient, and it does happen, that it contributes to observable retarded functions through loops. And so this is what we worked in this recent paper with Akash Jain in 2009, in September of last year. We classified the terms that appear in this effective field theory that do contribute to retarded functions, but which are invisible to classical hydrodynamics. Okay, so I'll skip the details about what these terms are. They will be derivative suppressed. You can look up the details in our paper with Akash from last September. But the point is that these extra terms, they in general will contribute to observable retarded functions through loops. The coefficient of those terms that are invisible to the constitutive relations at any order in the derivative expansion, and their contribution will be derivative suppressed. So if you want like a bird's eye view, the summary of this effective theory, so I will be finishing in a couple of minutes here. So the bird's eye view is like this. In this Schwinger-Keldysh effective theory, there are two types of fields. The classical field, which I call the R-type field, and the stochastic field, which are the A-type field. The effective action is organized order by order in this A-type expansion. So the terms that are linear in the A-type fields times some complicated function of phi R fields. So these are the non-linearities of classical hydrodynamics. So all the classical hydrodynamic equations with all the constitutive relations at all derivative order, they're hidden in here. The terms that are quadratic in the A fields, these are the terms that were present in Landau-Lifshitz. Some of these terms would be fixed by the fluctuation dissipation theorem in terms of the classical transport coefficients. There are other terms that are quadratic in the A-type fields that are invisible to classical hydrodynamics, but they're still Gaussian. And there are terms that are high order in the A-type fields. They're invisible to classical hydrodynamics, but again, through loops in this effective field theory, they will contribute to observable retarded functions. Okay. So the conclusions, like if you are lost with all this business of effective field theory, the conclusion is this: there are these parameters of the effective field theory that you can call them stochastic transport coefficients. They're fundamentally different transport coefficients than viscosity or conductivity. They're invisible to classical hydro at any order in the derivative expansion, but they do contribute to measurable correlation functions in the infrared. Okay. Though they're derivative suppressed compared to viscosity, and they're different from the usual long-time tails, because the normal long-time tails that people knew from the 70s, they're fixed by the viscosity and the conductivity. These are different kind of long-time tails that are fixed by these stochastic guys. Now, if you want to know the Kubo formulas for these stochastic transport coefficients, you want to work with non-retarded functions. The Kubo formulas for all the guys that we know, viscosity, conductivity, they involve retarded functions. These new coefficients need non-retarded functions. So the point is, knowing the macroscopic classical effective theory to all orders in the derivative expansion is not enough to correctly describe macroscopic infrared correlations. Again, if you want to go beyond the leading order in derivatives. Okay. So this is the end. I want to end with an encouragement for students in case there are any students left still. As a student, one often tends to think that all interesting physics, interesting questions in physics have already been answered many years ago by the great. Hydrodynamics is an ancient field by modern standards, and people are still trying to figure out some very basic questions. Now, if as a student, you work in a field that is less than 200 years old, do not lose hope. There are surely many fundamental things left to discover. Thanks for listening, and sorry to go over time.
Maybe we can unmute and clap. Thank you very much, Pavel. That was, I thought, a fantastic talk. We can, if Pavel has the energy, we can take some questions.
Yeah, have a little bit, yes.
Please go ahead, people.
So if I might, yeah, so for the last part, it appeared that the interesting new terms appeared from graviton loops. Is that correct? I mean, at least that thing which was like omega to the power 3/2, which didn't have the cutoff in it.
So these terms are here.
Yeah, right.
So these terms, they appeared from, if you wish, phonon loops, except they're not phonons of a solid. They are virtually excited sound waves.
So what was the like holographic interpretation of these terms?
In order to have holographic interpretation, you need to have graviton loop in the bulk of ADS.
Yeah.
This would the holographic interpretation would be the graviton loop in the bulk of ADS.
So so I just wanted to understand this term a little bit more. So they first of all, how come you are not writing the, okay, but here of course you wouldn't write, but I'm saying that there's a factor of h bar or some 1/n multiplying this term or not?
There's no factor of h bar. This term would be present even with billiard balls. But if you want to see what this term would look like,
yeah,
in a large M gauge theory,
right,
the coefficient here will be 1/n squared suppressed, or 1/n to whatever power,
right,
compared to this one.
Okay, and this term is independent of the lattice cutoff.
Correct. It's an infrared term.
This is an infrared term. I see. It's an infrared. But there is an interpretation of this term in terms of a bulk graviton loop calculation.
So if you want to work with ADS CFT,
right?
If you want to work with ADS CFT, you can interpret this term in the dual stringy description in ADS as the graviton loop in the bulk of ADS. But this term stands by itself without any ADS CFT. I mean, these terms exist for billiard balls, for water, it doesn't care if there's dual gravity exists or not. This term stands by itself. Now, this other thing that I was talking about, this is slightly different. So this second part of the slide here has nothing to do with ADS CFT. Okay, this is just normal 4-dimensional gravity, perturbatively quantized normal 4-dimensional gravity about flat space, and nothing to do with hydro, no black holes. Just look at interparticle potential and see, normal perturbatively quantized gravity. There will be a graviton loop contribution to the particle potential, and it will give a power law effect like this. So these two, the top part and the bottom part of the slides are just analogies. I'm not saying they're related to each other physically. I'm saying they're related to each other as analogies in terms of, both are similar in the sense that loops of massless degrees of freedom give rise to infrared effects that are more important than classical high derivative contributions.
I see. I see. And just one last question. That so if sometimes even in standard matter, not something like which has some large n, identifiable large n or something, but if you have a large number of particles, like Shiraz was saying, large number of particles, or let's say large density of the matter, then you know, these, okay, so this is infrared. So I'm a bit confused now. Okay, so I don't know how to.
Yeah.
Well, so one way to think about it is that in a large N theory, viscosity counts all the degrees of freedom that contribute to viscous, viscous friction.
Right.
So in a large N gauge theory, this will be N squared in four-dimensional gauge theory.
Yes.
Now, this, on the other hand, is only a loop of one sound wave. So this is order 1. And you can see here, eta over S is order 1. So this eta will be N squared, order N squared, and this term will be order 1 in the large N counting in a gauge theory.
So this would be suppressed even in like in a lab, in the lab, in standard experiments also, isn't it?
That is another question. Because if you ask about QCD, this is actually, this is some, we had comments about this in this paper with Guy Moore and Paul Romashka in 10 years ago.
Right.
Because there are also things here that depend on thermodynamics. You know, you need to know the equation of state to calculate how large this term actually is. And of course, the real world QCD, it has n is equal to 3, not infinity. Also, it depends what you take for eta over S. And we give some estimates there. And if eta over S is taken to be, 1 over 4 pi, then the effect of this term is not negligible. It's not like dominant. It doesn't, dominate everything, but it's also not tiny.
I see.
Sorry, could I ask also about the same term? Something here was confusing me. I had this very naive picture of a box of size L, where L is 1 over omega. I'm not sure exactly what this box is, but, and then I count how many particles there are in this box. And the answer will be n squared times L cube. And then if I think of this as a 1 over square root n effect, where n is the number of particles, I would have naively assumed, I would have naively obtained that this thing is suppressed compared to leading order by 1 over L to the 3/2, and that's sort of like this omega to the 3/2, so that's good. But then I would have assumed got a suppression of 1 over n, whereas your term is suppressed by 1 over n square compared to leading order in the context of a large N gauge theory. And that somehow tells me my picture is wrong, and I just wanted to know if you had comments.
Yeah, I think it's maybe okay. So I don't have an intelligent answer to this, unfortunately. But what I can say is the effect is not just the 1 over n suppression of statistical fluctuations in general. It's also an effect that involves the mean free path of the collective fluctuation, which is the viscosity.
Right.
Which is determined by the viscosity.
Right.
And the suppression that you are talking about would also be there in Euclidean physics. But this is somehow more special to real-time physics than to Euclidean physics.
And this seems less important than the suppression I'm talking about, because it's more in the large N theory, because it's 1 over n square suppressed compared to leading order. So is the effect that I'm talking about, is that seen somewhere? Is there a 1 over n suppressed term?
Well, that would be like the no. I think the effects that you're talking about, they're more like the effects of well, I don't want to say heat capacity. Yeah, I wanted to say heat capacity because it's the heat capacity that measures the fluctuation of energy in the canonical ensemble.
And that should show up somewhere. There should be some term, if I look carefully, to see that is not. I know you're looking at distance suppression, but suppose I was also interested in 1 over n suppression. I should see a term that was 1 over n rather than 1 over n square suppressed. I ask because normal loop counting sounds like it would give you a 1 over n square suppression, as you say, in the bulk.
Well, in the bulk of AGS,
right,
this will give 1 over n squared suppression, I think.
Would give 1 over n square suppression. Here, if you look at just 1 over square root number of particles in a box, that is 1 over n suppressed, right? So that's such a universal kind of thing that it should show up somewhere. And I was wondering about the mismatch between these two expectations. I'm sorry, it's probably a stupid question.
No, it's not. No, I understand the question. Yeah, I would have to think more. Sorry.
Right. The loop would have to know that there was a black hole. That would somehow be important. It's like the Hawking rate. Okay, anyway, please, I'll thank you. Can I ask one? Sorry, first, anyone else with any other questions?
Shiraz, I have a question if you allow.
Please. As long as Pavel doesn't need to sleep.
Yeah, Pavel, do you have anything? Is that fine?
Yeah. Please go ahead. Yeah.
So going back to my previous question about the first part of your talk, 16 parameters and the fluid gravity correspondence. So I wonder what is happening on the bulk side, on the ADS side. So you said that the Landau formulation of fluid is not.
Is my connection off?
No, I think, Amitabh, I think we just lost. You were saying, you said that the Landau connection of fluids is not, and then we couldn't hear you anymore. Are you still there, Amitabh?
Amitabh froze.
His internet has. Maybe we can take another question while we're waiting for him. Anyone have any?
Yes, sir. Okay, it's just a random question regarding this this polynomial tail. Okay. In flat space, LS for scalar, in the spherical harmonics, okay, there are polynomial tails. This is a work of Price from 1970s.
Are you talking about this?
No. There's t to the power minus 3.
This one.
Yes.
I think the question is that in flat space, you look at the quasi-normal, the fall off of correlation functions is power law. This is this Price theorem, unlike an ADS. And the question is there a connection between what you say?
Is there some connection?
No, I don't think so. Because that comes from classical physics, right?
Okay.
Right, and this is specifically non-classical. I mean, by non-classical, I don't mean quantum. I mean statistical. You need some kind of path integral.
Okay, thank you.
Amitabh, are you still around? Can you? I think he's exited. Okay, right. Any other questions? Okay, could I ask a quick question about the last part of your talk, please?
Yep.
The part with the double degrees of freedom and so on.
Yep.
The first question is a very general one. As you said, when we're trying to write down some sort of effective field theory, perhaps the most important question is what are the variables? And then the symmetries and the equations of motion and so on.
Mm-hmm.
So these new developments that you referred to over the last 5 years have made some made a claim about what the new the effective variables are for this real-time Schwinger-Keldysh contour. I wanted to understand what your view is about the status of this claim. Has that claim been derived? Or is it postulated?
I think it's postulated. I think it's postulated based on this highlighted kind of part here of the slide. It just says we want to have an generating functional that is gauge invariant, and how do we do this? So we say, okay, let's introduce this combination A plus partial phi, the Stuckelberg thing. And then if you say that phi is the dynamical degree of freedom, then this procedure buys you two things. It buys you gauge invariance, and it buys you the fact that the equation of motion for phi is the conservation law as you want. Okay, so that is I think it's reasonable, but I hear you is that the claim is postulated.
And I wanted to hear from you what it would take to understand at a more fundamental level. Imagine we started from a field theory path integral. We know what we're doing on this Schwinger-Keldysh contour.
Yep.
Can one imagine in a toy model actually seeing how this comes about? Or has anyone tried this? Or I mean, can you imagine how it might work?
Shiraz, if I may interrupt. Hi. I've thought about these things a little bit, and I think, the thing that you would be asking is take I don't know, a quantum particle or something, and just take this microscopic theory. It could be a gauge theory, it could be the full standard model if you want, and show that in the low energy regime, this theory boils down to the Schwinger-Keldysh theory in some sense.
And I don't mean, I don't have a very high standard. I just try to
understand
roughly what kind of change of variables, where it comes about, roughly.
Yeah, so there are comments about this in Hong Li's original papers, and what would be needed to be done would be that there will be a sort of a decoupling between low energy modes and high energy modes. You'll have to first identify what parts of, you'll have to take this theory, which is thermal. You have to thermalize the theory, and somehow you have to introduce a temperature scale and then do a decoupling between low energy and high energy degrees of freedom, and then perform a path integral over all high energy degrees of freedom.
Well, but Shiraz wants a formula that relates this phi here to the microscopic standard model fields.
Right? For instance, can we do it even in equilibrium? Can we? I know that there are some kinetic theory derivations where you try to identify what individual transport coefficients are in terms of the microscopic kinetic theory variables. So even there, we can only do it in weak coupling and this sort of kinetic theory regime. So already doing that in normal classical hydrodynamics is hard enough. So I'm not sure how would you go about taking a toy model microscopic theory and actually performing this procedure. I understand the question. It's just I don't think there are any.
Where in the path integral at what step would these new variables ever be introduced? I just want some rough feel.
Okay, in my opinion, at some point you will take your original degrees of freedom, let's say a scalar field theory, you start with some scalar field theory and you put it at finite temperature, and at some point you will need to take this original degrees of freedom and identify what are the low energy modes and what are the high energy modes. And it will be an interacting theory, and you'll have to find out which are the low energy modes or the high energy modes. And at this step, somewhere these phi fields should emerge. But obviously, this is the shot in the dark, because this is the only logical place where these can appear.
Good, and the same modes will have to appear in every theory, right? It's very universal.
And the claim will be that this is, and just like the claim is that hydrodynamics is universal, because you're starting with this theory on symmetry grounds, you would hope that no matter what microscopic theory you start with, given in a certain regime of applicability, high temperature near equilibrium, these modes will universally emerge.
Well, the thing is, at zero temperature, you can argue that the relevant modes are the Goldstone bosons. Okay, so here this is thermal physics in real time. I don't necessarily know how to think about Goldstone bosons in this way. I mean, okay.
Sorry, that was a very vague question. I'm sorry.
So Shiraz, to this question, I would like very much to understand that myself. Do I find the situation unsatisfactory? I do. I want to understand this myself.
I mean, for instance, in some papers, in some of these papers, there's this claim that they are somehow deriving the second law of thermodynamics. But this is not really a derivation. This is a contextual derivation in the sense that this derivation only exists in the context of this already IR model that people have proposed, in which there are certain degrees of freedom. It's a consistent model, but it's a consistent IR effective theory. And in this consistent IR effective theory, you have a sort of derivation of the second law. But if you are expecting that there is a microscopic understanding of how the second law emerges universally in any near equilibrium thermal system, then that is not a question that has been answered using these models.
Sorry, a sub part to this question, I'm sorry, and I'll stop here. But it is within ADS-CFT, we might want to derive this at least, right? Assuming ADS-CFT is correct, then the question of the derivation becomes a very clean question. And I know there's been some work on this recently. Has this more or less been done?
So yeah, in this context, now we are talking about a very specific question. Right now we know what is a microscopic model. It's the model that is described by holography. And in that particular model, we could ask the question if there is a derivation of the second law.
Yeah, I'm not talking about the second law, sorry. It just, or maybe eventually the second law.
Yeah.
No,
within ADS-CFT, we know the second law, right? It's Hawking's area.
Yeah.
I meant just this path integral with these double degrees of freedom. I know there's been some work on this recently, Hong Liu and collaborators.
Yeah, Hong Liu and company have I think even most have a paper on this holographic string.
Lognagam and friends have a paper on this as well. Yes.
I mean, there are like a couple, all groups have a paper on like holographic interpretation of the Schwinger-Keldysh actions.
Right. So what I wanted to know is, in your opinion, has this formalism been satisfactorily derived out of ADS-CFT?
And I would say no. Like right now, the status of these holographic models is that the proposal of the model and identifying the degrees of freedom. I don't think there has been a derivation of the effective action at the boundary using the holography.
But at least this is a completely well-posed question, right? Because ADS-CFT, we know the rules of that system. It's just analyzing partial differential equations. So if this is correct, or analyzing path integrals, if this is correct, we should be able to derive it without any assumptions from there. Do you agree with this, or is that wrong?
Yeah, I mean, I agree, but the fine print here would be that already, I mean, we know that the ADS, the ADS dual corresponding to a thermal state would be like a black band. Now, what we want is like somehow there has to be a different kind of state or a different kind of like for non-equilibrium perturbations. What is a holographic dual, which will incorporate these double degrees of freedom and things like this. And this is what some of these recent papers have tried to propose. Like there's just like some sort of dual, like some sort of doubling that happens in the bulk as well. And,
well, it's more than the doubling. Like this path integral, in particular, the correct integration measure, like when you say that's the degree of freedom, okay, so you need to specify the integration measure. So the correct integration measure for these degrees of freedom, it has to emerge from the path integral over the stringy degrees of freedom in the ADS bulk. And from what I understand, Shiraz, that's what you want to do. And that should
that's
be
what I would like, yes.
It should be, yeah, in principle, as a matter of principle, yes.
Okay, yes. Okay. Thank you so much. Sorry for the disruption and over many questions.
No, it's great. Sorry, I'm falling into the equilibrium state.
Okay, so we shouldn't delay the onset of equilibrium any further. So thank you so much. This is I thought it was a fantastic talk. Thank you so much.
Thanks a lot. It's really a great talk. Enjoy.
Yeah, thank you. Good. Yeah, was pleasure for me. Okay, I'll go full into my ground state.
Okay, excellent.
Yeah, thanks everyone.
Bye.
Bye-bye.
See you. Bye.